All right. I will begin. I will try to begin. Hello? Can I talk? I can talk? All right, I will start now. Dear Father, we thank you for this day. Thank you for the students. Just ask you to, again, bless our work, help us to glorify what we do, and just understand a little bit more about physics today, Lord. In your name I pray, Lord Jesus. Amen. So I thought I'd talk about the relative motion problem again. And so the setup here is there are two frames of reference. All right? The one, we can think of the one as sort of like the fixed frame. All right? In some sense, that's a matter of perspective. But suppose you have x, y, z. We'll think of that as a fixed, not moving frame for the sake of discussion. All right? And then we have a second frame of reference, second coordinate system, which I'll call x bar, y bar, z bar. Up here, perhaps. All right? So here's x bar, y bar, z bar. All right? And essentially, and we're assuming that they have the same orientation for the coordinates, the x directions. All right? So like, I'll write equation for just a second, but so like this here is, let's see here in my notes, I denote that by r sub 0. All right. And great. So if we have, let's say, a point that we're describing we're describing the trajectory of some physical particle, some object. Maybe it's like, here's the path of the particle, right? This is not in the notes, but suppose this is a trajectory. Then I've got choices. I can either describe a point with the coordinate vector r, let's call this s. So, or I could describe it with the coordinate vector relative to the barred frame. All right, so here's my mass. So I'm saying that two coordinate systems. On the one hand, I have S, which has Cartesian coordinates x, y, z. On the other hand, I have my moving frame of reference, S bar, which has coordinates x bar, y bar, z bar. These are in some way related because I'm assuming that x hat is equal to x bar hat, y hat is equal to y bar hat, and z hat is equal to z bar hat, which is to say that, again, we can obtain the coordinate axes by like a parallel translation. So I'm not considering like a rotation like I was last class at one point, all right? So if this is the situation, we can just use vector addition to relate the coordinate systems, right? So to get to this point M, I've got choices. I can either say the coordinates as measured in S are equal to what? They're equal to the coordinate of the origin of the moving frame plus the position relative to the moving frame, which is this, right? That's just vector addition. Do you guys see it? So I can go like here, or I can do R naught plus R sub S bar. Two different ways to describe the same place in space, right? These two different competing descriptions of the trajectory, either in terms of the S frame or the S bar frame. Conversely, I could just as well write what? I could just write R sub S bar is equal to what? It's equal to R sub S minus R sub naught. I could also do that. I could describe the motion in the moving frame in terms of the given motion in the unmoving frame subtracted from, well, minus the position of the origin. Notice that there's like a complete symmetry here, see, because where is the origin of the S frame in terms of the S bar frame? like R naught is, let me write this out in words. So this is where the S bar origin is in view of what? Of the S frame, right? That's the position of the origin of the barred frame and the unbarred frame. Conversely, if you look at this, you notice that minus R sub naught is the position of the origin of the S frame with respect to what? The S bar frame. Right? Because if I start here and I ask where the origin of the black frame is, it's over here. That's the opposite vector to the R naught. In some sense, neither frame is really preferred. I could just as well have said the bar frame was unmoving and the other frame was moving, you know? It's in some sense a matter of perspective. Okay, but anyway, once we have this, then we differentiate. And so if I differentiate, I get dr sub s dt is equal to dr naught dt plus dr s bar dt, right? And what does that tell us? That tells us, in other words, that the velocity measured in the S frame is equal to the velocity of the origin of the moving frame plus the velocity measured with respect to the moving frame. And if we differentiate again, we get what? We get, you know, d squared r dt squared, there's an s here, is equal to the second derivative of r sub naught with respect to time plus the second derivative of r sub s bar. I'm just differentiating again, okay? And this tells me that the acceleration in the S frame is equal to the acceleration of the origin plus the acceleration of the S bar frame as measured with respect to the S frame. So this is the relation. Now, so what I said is that then the continuing, I said if, let me write over here. I said if, you know, S is an inertial frame of reference with net force F acting on M, then Newton's second law says what? Newton's second law says that F is equal to mass times acceleration. But here there's a question of which acceleration I'm talking about. Which acceleration am I talking about? I'm talking about the acceleration in the fixed inertial frame of reference, which I'm telling you is the S frame. So A sub S. All right? But how is A sub S related to the acceleration in the moving frame? See, I can substitute in here. I can plug that in over here, and this gives me mass times the acceleration of the origin of the moving frame plus the acceleration measured with respect to the moving frame. All right? And so this then, if we do the math, tells me that the mass times the acceleration measured in the moving frame, all right, is equal to the force measured in the inertial frame, right, minus what? Minus the mass times the acceleration of the origin. And that's why there's a minus there. Because one of you guys asked me why there's a minus there. It's this algebra. Let's look at an example maybe. Let's think about a boat on a river. All right, we'll think about a boat on a river. We're going to suppose that the boat is going across the river And relative to the river, the boat is going directly, let's suppose that the river goes north-south. All right, I'll draw a picture here. So, example 1, we've got a river, all right? And it's flowing, say, it's a fast river, 20 miles per hour. Miles per hour, what am I talking about? Let us not do that. Meters per second, there we go. It feels better. So we have meters per second, we have a boat, river is flowing like that, 10 meters per second upward, all right? And at the same time, you got a boat that starts here, all right? And the boat is traveling, let's say, 3 meters per second, and the boat travels 3 meters per second eastward. All right. Now the boat travels 3 meters. When we say that the boat's going 3 meters per second, let me be more complete. What I'm saying is it's going 3 meters per second with respect to the water that it's in, right? So we can imagine, we can relate. Let's see here. Trying to think. So my picture didn't get too busy here. So let's suppose that I can make a fixed inertial frame of reference like y, x like this, right? And then I can think about a frame that moves with the boat. So I'm just going to let the boat. I'm thinking about a frame of reference that moves with the river. So this is my S frame, and I'm saying that the S bar frame moves upward, right? So of course, as the boat moves, what happens? It does something like this, right? Right, as it goes over, the river pushes it up. Yeah. All right. So without getting too mired in the mathematics here, let me just get straight to like what we should say, which is that the velocity of the boat with respect to S, right, is equal to the velocity of the boat with respect to S bar, right, plus the velocity of the origin. So here this is my moving frame of reference. Right here is where R sub naught is, okay? So what's the velocity of the frame of reference? I'm thinking about this frame co-moving with the river, right? It just moves up like that. The X bar, Y bar system moves up with the river. What's the V naught? So I heard now, but what's the direction? It's what? It's a vector, right? 0, 10 meters per second, right? And what's the velocity of the boat? Well, I told you it's going 3 meters per second eastward, right? So it's 3 meters per second, 0. That's the velocity of the boat with respect to the river. So what's the effective velocity of the boat in all this? With respect to the shoreline, it's actually going faster than 3 meters per second, right? It's actually going, at a speed which is faster than just 3 meters per second. That's its velocity with respect to the shoreline, right? We're fixing this point for the origin of S, and we're letting this other coordinate system track up the river. Now, you don't have to draw X, Y, and X bar, Y bar to do these problems, right? Once you have an intuition for this, you can just write this down, and I would be fine with that. Like, I don't require you to write this picture over here to justify what we're doing. I'm just saying it's part of this larger discussion, all right? So there you go. I mean that, and then we could answer all kinds of questions, right? Like, if I gave you how wide the river is, we could figure out how far it goes upstream and all kinds of questions like that, right? Let's go on to the next example, though. I think we've seen what we need to see here. So example 2, if we have, an elevator like this, right? And let's suppose that the R sub naught is basically, so what I'm suggesting here is maybe we should think about a frame of reference that co-moves with the elevator, right? Like I can think about y bar, x bar moving with the elevator, and if I, put something in the elevator, whatever, usually I like to think about I don't know. I guess I'll put a Pac-Man. That's all I've really left myself room for. But you put a Pac-Man, and it's on a scale, all right? And Pac-Man's on this scale. All right, great. So, what's the story here? If we measure the force on Pac-Man, what is it? So, the other thing is, I'm making this needlessly complicated in the sense that I really have no intention of doing anything with x. We could just talk about y, right? So let's do without the vectors here. Let's just think about y. It's a one-dimensional problem, right? So this is just going to be positive is upward, okay? And if I do that, what's the net force on Pac-Man? What's going on? If he's sitting on top of a scale in an elevator, there's two things going on, right? Gravity, yeah, and so we've got gravity, which is the mass of the Pac-Man and downward, and we've also got the force of the scale pushing back up, right? Which we would call the normal force, but more on the normal force after test 1. All right, this is pretty much as far as I'm testing on that, and here is this example. So we've got, the scale force, right, minus mg. That's the force that's on the Pac-Man, right? Scale pushes up, and gravity, of course, pulls down. Now, the mass, let's see here. So if we follow the derivation we just did, what's the relation? How does the acceleration work? Mass times the, so we have the mass of Pac-Man times the acceleration in the barred system, right? Which I'll just call a bar here because there's only one dimension. So the mass times the acceleration with respect to the elevator is equal to the force applied, which I've called F Pac-Man, right? Minus what? Minus m times the acceleration of the elevator. Right. So let's see here. What is the acceleration relative to the elevator, though? If he's moving, he's not jumping in the elevator, he's not going through the floor, he's just sitting there in equilibrium with the scale, right? So the acceleration relative to the elevator is 0 because his position is fixed in the elevator. In fact, his velocity relative to the elevator is also 0. So this is 0. So we have 0 is equal to, the scale force minus mg minus ma naught, which we can solve. And that gives us what? The scale force is what? Actually equal to m times what? Times g plus a0 if we do the algebra here, right? So if this elevator was like the elevator in this building, you could put a scale on the floor and you could stand on it, and it would tell you your true weight. Because the elevator in this building does not accelerate. It is, as far as I can tell, it doesn't accelerate. I feel no motion in it. Right, I get in, and a half a minute later, I'm like the next floor up, right? So, I mean, it must be accelerating, but I can't feel it. But if you're in an actual elevator, like the ones over in the Runken Pratt, right, you can feel that, right? Those move. We need to somehow transplant those into this building. Along with, we need to like cut a hole to insert another elevator shaft somewhere. Or maybe free up some doors in various hallways. Like, the stairwells here are very perilous. Like, you never know what you're going to get. You're like, I think I'll go down to the second floor. Oh, no, sorry, can't exit second floor here. It's like, it's really complicated, you know? I guess that would probably, maybe it's for engineering, so that if you guys have like optimal path problems in this building, it's actually really, really sophisticated to figure that out, but yeah.
So why does it go from mass time acceleration, initial acceleration to mass times gravity minus mass times? Like, why did that get broken up into two?
Well, we had up here that the net force was the scale force minus mg. It's because scale force acts up, mg acts down, so that was that. And then I just substituted that. I did just to put this is that. I plugged it in there. The reason that it's minus ma naught is that over there. But after everything settles here, it makes sense, right? If the acceleration of the elevator is minus g, what's the scale force? 0, right? So if you're weightless, that means the elevator's free falling, probably bad. On the other hand, if you weigh twice as much, that means that the accelerator is actually going upward at a g. I'm sure such an elevator exists in some sort of skyscraper somewhere, but like, you know, usually I think it's probably just, 20% of g maybe at most, something like that. But all right. So I talked about this on the projector, but I think it's good for me to take some time to just work it out carefully, so we did that. Now I'm going to turn the topic over to circular motion for a bit. Now, we study circular motion in more depth at the end of this course, right? But at the moment, we really just have really one thing to work with, which is that the acceleration, we can break into two pieces, right? There's the centripetal part and there's the tangential part. And the centripetal part is based on the velocity squared divided by the radius. Excuse me, the speed squared divided by the radius, I should say. And so if we're talking about constant speed circular motion, the acceleration simply has to be, in terms of magnitude, equal to v squared over r. And I think that's interesting to think about, to try to gain a better understanding of why is it that we don't have to worry about that for the problems that we're working this semester, right? Like, if the acceleration, so constant, let me just write it. So we worked this out from like, you know, calculus of paths, whatever you want to say. So the acceleration was the change in speed with respect to time times the unit tangent, plus the speed squared divided by the radius of the curvature of the motion times the normal. So that's the formula for acceleration in general. So if I had if the trajectory was something like this, what that means is that the acceleration can be broken into two pieces. So this is the acceleration. There's two pieces. There's the tangential part and there's the center seeking part. So the tangential part points in the tangential direction, like this. Let's see here. So for this, it would be something like this. This would be dv dt times the unit tangent, right? But there's also a, if you can picture it, a center seeking, a centripetal component to the acceleration, which looks like, I guess, like this, all right? So something like this would be v squared over r times n. So the sum of the red and the blue vector should give you the net acceleration. There's only a tangential and a normal component. These are perpendicular, so our formula for the magnitude of the acceleration was given to be the square root of the derivative of the speed with respect to speed squared plus v squared over r quantity squared. All right. So I want to look at some, often we have dv dt is equal to 0, which is to say we have constant speed, circular motion. Constant speed circular motion. It's a very common case. In that case, the acceleration has to be directly center seeking, right? Oh, here, if you could add a date to this, would be awesome. Who knows, maybe I'll even get the top hat working before we leave today. Tell you what, I'll take a second, I'll do it. I know you guys got to have your top hat. I understand. I hear what the people want. I give people what they need. I can't stop, won't stop. What? Yeah?
One of those is perpendicular to the tangent.
The normal is perpendicular to the tangent. The normal, and it's the center seeking normal. It's called the Frenet normal.
Okay, and that is the sum of the two parts of that?
Yeah, like I wrote here, the acceleration is the magnitude of the blue vector is the change in the speed with respect to time, infinitesimal change, the derivative, and the magnitude of the normal piece is the speed squared divided by the radius of the curvature. So if I could, yep. The normal vector. It's called the Frenet normal, F-R-E-N-E-T, center seeking normal. We defined it as the normalization of the derivative of the tangent vector with respect to time. If you needed to calculate it, that's what it is. With respect to typical examples, though, oftentimes we're going in a circle, so the norm n is just the center seeking vector. It points to the center of the circle. I'll draw a picture just here a second. N is the normal. But it's not a normal. It's not a normal like this, right? It points to the center of curvature. It's not, so we use the same word, unfortunately, but what's the osculating circle for a plane? The answer is, I don't know. See, that's the funny thing, is a line escapes that discussion about the Frenet, the TNB frame. Like, lines are outside that discussion. Lines are too simple for the Frenet frame, the TNB frame. Like, what's the curvature of a line? 0. So what's that make the radius? If the curvature is 1 over the radius? Infinity, right. So the line has to, you get lines in some sort of like limiting context. So here we got 3615 is ye old top hat code. There you go. Okay, so example. Example. I do have an example. All right, so example 3. Earth. All right. Let's find acceleration at equator due to Earth spinning. So if I was to draw a picture like this, right? And here's the North Pole, perhaps, all right? But I probably shouldn't write that, because then you'll think that's the normal, because I would write an N. We only got so many letters. I'm sorry. It is what it is. But this is like from the North Pole down. So if you can imagine, this is the equator, a top view from the north looking down on Earth, right? And so if I put a person here on the equator, the distance they are from the center of the Earth is the radius of the Earth, right? And the Earth is spinning like this, right? Actually, I don't remember if it's, don't ask me. I honestly don't remember if it's spinning clockwise or counterclockwise with respect to the North Pole. Which one is it? It's clockwise. The good news is it doesn't matter to this calculation.
It actually does, because God made it go one direction.
So v squared over the radius of the Earth is equal to the centripetal acceleration. Right? This is the centripetal acceleration relative to the circular motion. How big is this? So how do we figure out, I mean, this is the centripetal acceleration for the Earth. So how long does it take, like how do we calculate this? How about, well, so we got what, 2 pi r, and what's the period? It's constant speed, right? Like the Earth rotates at the same speed, right? It's not like different rotational rate, different times a day, right? And how many seconds are there in the day? Well, everybody knows there's 86,400 seconds in a day. And so I have the distance divided by the time, that's the speed, since it's constant. Got to square that and divide by the radius of the Earth again. 86,400 is 60 times 24 times 60 again, I think.
Is this still open? Is this like still open to you on the test? Like is this going to be?
Yeah, this could be on the test. Absolutely, sure. Certainly. So if we look at this V alone, I crunched the numbers in the book, and in my notes rather, 2 pi r over 86,400, it works out to 463.3 meters per second. That's how fast. I mean, that seems that's a lot, you know. And that may not mean anything to you. It doesn't mean a lot to me. But 463.3 meters per second, that translates into about 1,036 miles per hour. That's how fast you're spinning. Like that's your tangential speed relative to the Earth spinning on the equator. All right, just go around. That sounds like a lot, but what is this red quantity I wrote up here? What's that work out to? Well, this is actually, so if I put that number in, I get 463.3 meters per second. Got to square that. I got to divide by the radius of the Earth, which, by the way, is about 6,371 kilometers. And when you crunch these numbers, what you get is 0.034 meters per second squared. So that's the centripetal acceleration. If I was to draw a picture, let me draw Mr. Top Hat over here, right? That's the net acceleration of Mr. Top Hat, all right? Like, well, let me draw a picture again over here. So if I make it bigger. So what I'm saying is that if he's on the equator, the net acceleration, where's the center of gravity for Mr. Top Hat? Maybe here, I don't know. So the mass times acceleration has to be equal to 0.034 meters per second squared. And whatever you want to make this, say minus y hat, we can go with that, right? That's the net the acceleration is that. And that's still equal to what? What are the forces at play here? Gravity, right? So you got yourself, mg in the minus y hat, and then what? So the other force, there are only two forces at play, right? If there wasn't this other force, what would happen to Mr. Top Hat? Where would he go? He would fall into the Earth, right? So what's keeping him from doing that? The normal force, right? So normal force, like that. So this plus the normal force is equal to that. Yes?
In the second part of that, like, long equation, you can't just have acceleration and you don't have mass in there anywhere. What happened to the mass?
Oh, it's coming. Thank you. Excellent question. So you notice what this all means is that the normal force, right, is what? It's actually equal to, mg, right, minus what? Or plus rather, plus 0.034 meters per second squared times the m, which you just told me about, right? Let me factor the m out if you guys don't mind. So we've got m times all that in the y hat. And I think, let me think about this for a second here. Minus, I want to make sure I didn't make a sign error. They shouldn't both be plus if they're on the same side of the equation, right? So if I solve for Fn, I should have what? I still have the minus on the 0.034 term, right? Right? So what's this all mean? This means that if you weigh yourself at the equator, the normal force that the scale, works off of is what? It's not as big at the equator as it would be, say, at the North Pole or something, right? You're losing some of the gravity effectively, at least as it's perceived by standing on a scale, you're losing 0.034 of the 9.8. But this is pretty much negligible, so we ignore this. But technically speaking, the effective acceleration you experience since you're actually, stuck on the Earth rotating around the north-south pole axis, I think there's actually a distinction between the magnetic north and south versus the rotational north and south. But anyway, these nuances aside, it doesn't matter that much because G is much bigger than this effect, all right? So, what's the other kind of spinning we're always doing? Do you guys know? We're also rotating around the sun, right? And so if you think about that, if I can draw a picture eventually. So one of the things I'm saying, by the way, is because we're going in a circle around the axis, our net acceleration is not technically zero. Even though I'm not moving, because I'm going in a circle, that means I have a net centripetal acceleration towards the center of the rotation around the circle, which I'm rotating. Yep.
So if you were standing on the pole,
Yeah.
then would it be
Yeah. If you're standing on the pole, then there's no circular, no centripetal acceleration there. Yeah.
even though you're spinning around?
That's right. Yeah. That is right. Because while you are spinning around, you're not really feeling it because it takes you a day to turn. I mean, it's like a whole day for you to rotate, right? The reason that you can even calculate this, and I don't know if you could feel that or not, but understand that, yes, it's also a day, but it's a day that you're going 25, how long is the circumference of the Earth at the equator? What, 25,000 miles? I forget. It's a lot, right? It's enough that you got, well, we can figure this out, about 1,000 miles per hour, 24 hours. So yeah, it's about 24,000 plus miles around the circumference of the equator, right? So you're going that whole distance if you were there in one Earth day. Yeah, go ahead.
In the last equation,
Uh-oh.
why does that only apply to acceleration?
Am I missing a bracket? I am missing a bracket. Let me make that clear. This goes to there because it's a vector. It's on both of them. Thank you. Very good question.
And when the gravity
Uh-oh.
for G, would
Slip
G
that
be
here.
positive 9.8, or would that be negative 9.8?
G is always the number 9.8 meters per second squared in here.
Okay.
And I put the direction in with the picture or with a minus or something. So here I put the minus y hat to indicate that it's that way. I'm taking
So like if I was to plug this in, I would just plug in 9.8, not negative 9.8. You already
it. It depends on which equation you're looking at. I can't answer that with authority. Yeah. But probably what you said is what is correct. So, okay, so example 4. If we have the sun, there's my very exciting picture of the sun. And if we look at the radius of the Earth's orbit, you know what that's called? Earth. All right. How far is it from the Earth to the sun? What'd you say? 93 million miles? Is that right? So the answer is one, man, I forgot the notation for it, but it's 1 astronomical unit. But that's just a lazy way of me telling you it's about 1.5 times 10 to the, let's see here, I don't remember this off the top of my head, times 10 to the 11th meters. Now, of course, this is, well, you know, is the equator a circle? Not exactly either, right? It's actually kind of lumpy. There's a certain amount of lumpiness to it. But if you look at it from space, it's pretty close to a circle, you know, or at least that's what the conspiracy is. But all the pictures seem to consistently indicate it's some sort of oblate spheroid with a pale blue color. Anyway, so the radius of the orbit is about 1.5 times 10 to the 11th meters. And how long does it take the Earth to get around the sun? 365.25 days, right? So the velocity of the orbit of the Earth around the sun is something like 2 pi radius of the orbit, right? Divided by 365. I'm sorry, I'm shorting you your leap day. 365 times 86,400 seconds, which, if you do the math, works out to, wowzers, 29,885. Man, surely we can feel this. 29,885.8 meters per second. Good grief, why can't we feel this? That speed is tremendous, right? It's a tremendous speed. We should feel this, shouldn't we? But what's the deal? What's the centripetal acceleration in this motion? Yeah, exactly. It's the radius is what? Ginormous. So radius of the orbit. And when we crunch these numbers, we get 0.00595 meters per second. So this acceleration is even less perceptible than the relative spin motion around the axis of the Earth, right? It's such a small acceleration that you would have to be very, very, you'd have to have a very sophisticated experiment to pick up on this kind of motion, if you even could. I don't know. Okay, truth in advertising here. Does the Earth actually rotate around the sun in a circle? No. What does it actually do? It's an ellipse. And does it even make sense to say there's a center of the ellipse? But how does that ellipse relate to the Earth and the sun? Do you guys know? No. So the truth of the matter is, to the best approximation of Newtonian mechanics, the Earth, the sun, all of the moons of the Earth, okay, there's just one. You know, you got your what? You got your Mercury, you got your Mars, future Elon, Elon's place there, and where else we got? There's a Neptune, I've heard. There's that Uranus that they labeled poorly. You got your Pluto. What else you got? You got all kinds of moons, right? All this stuff. take all of that. Somewhere, if you take that and you take the average of all those positions, the weighted average, there's a center of mass of all that stuff, right? Everything rotates around that center of mass. That essentially defines an origin, and with respect to that, there's ellipses that all of the planets travel around that. Of course, the motion of moons is more complicated because they're also rotating. They're also orbiting a planet, which is itself rotating. So it's very, very complicated in the totality, but it can all be derived with Newton's universal law of gravitation, which we talk about towards the end of the course. But anyway, that's all I got for you guys for the first test. You guys have any questions about anything? Nobody? If not, enjoy your weekend.